Assalamualaikum dear students. In this video we are going to cover the section 10.2, the same chapter we started in last lecture, chapter number 10. This is about graphs. So 10.2 is about graph terminology and special type of graphs. So here is the section summary. Basic terminology, some special types of graphs, bipartite graphs and new graphs, old graphs. So first of all, the definition of uh, adjacent vertices. Now two vertices U, V in an undirected graph G are called adjacent or neighbors in G. If there is an edge E between U and V, such an edge E is called incident with the vertex U and V, and E is called connect U and V. Like if we have two edges U and two vertices U and V, and then we join these by an edge. So two vertices U and V are, in undirected graph are adjacent. So U, V are adjacent. In G, if there is an edge E between, so this is the edge E between U and V, such an edge E is called incident. So this E is the incident with the vertex U and V. Okay, and E is said to connect U and V, right? So there is a next definition: the set of all the neighbors of a vertex V of uh, the graph G, denoted by NV, is called the neighborhood of V. If A is a subset of V, we denote by NA the set of all the vertices in G that are adjacent to at least one of the vertex in A. So NA is equal to union of NV, where V belongs to A, where A is the set of all the vertices, right? Definition 3. The degree of the vertex is in undirected graph is the number of edges incident with it, except that a loop at a vertex contributes 2 to the degree of the vertex. Now the degree of the vertex V is denoted by degree V. So here is an example. Here we have two graphs G and H. What are the degrees and the neighborhood of the vertices in the graph G and H? So first of all, degree of A. So degree of A is 2 because it is adjacent to B and F, that is two vertices, right? Similarly, degree of B, here is the vertex B. So degree of B is equal to, now it is adjacent to C, adjacent to E, uh, adjacent to F, and adjacent to A as well, right? So it is adjacent to 4 vertices, so degree of B is 4. Similarly, you can find the degrees of other vertices as well. Now in H, there is a loop, okay? So let's find out the degree of B. So degree of B is equal to, this is the B is adjacent to A, B is adjacent to D, B is adjacent to C, okay, and because of this loop now, and B is adjacent to E as well, so we have apart from this loop, B has 1 2 3 4 neighbors, right? So because of this loop, we'll add 2, so the total number of neighbors is 6 now, so degree of B is 6, right? Next theorem, theorem number 1. This is very important theorem in application of graph theory, handshaking theorem. So if a graph G, the set of vertices and edges, is an undirected graph with m edges, then sigma degree V, that is the sum of degree of all the vertices is equal to 2 times number of edges. So it can be thought of the graph where vertices represent the people at a party and the edge connects two people who have shaken hands, right? Handshaking theorem examples. How many edges are there in a graph with 10 vertices of degree 6? Now, since the sum of the degrees of the vertices is 6 multiplied by 10, so this is equal to 60. The handshaking theorem tells us that 2m is equal to 60. So, what is the number of edges? M is equal to 30. Okay. So, again, if a graph has 5 vertices, can each vertex have degree 3? Now it has 5 vertices. Can each vertex have degree 3? So this is not possible by Handshaking theorem because the sum of the degree of the vertices is 3 multiplied by 5, which is equal to 15, and this is odd. Okay. Okay, degree of vertices. Theorem number 2. So an undirected graph has an even number of vertices of odd degree. So this is also a result to remember. An undirected graph has an even number of vertices of odd degree. So let's assume V1, sorry, V1 be the vertices of even degree and V2 be the vertices of odd degree in an undirected graph G uh, with m edges. So number of edges is m. Now according to handshake theorem, we have 2m is equal to the sum of degrees of all the vertices. So this is equal to degree of all the vertices in V1 and plus degree of vertices, sum of degrees of vertices of all the vertices in V2. So what we assumed, V1 be the vertices of even degree. V1 is the set of vertices with even degree, and V2 be the set of vertices of odd degree, right? So if it must be even because every vertex has even degree, so it must be even since degree V is even for each V. So this sum must be even because 2m is the sum. So even plus odd cannot be an even number. So if this is even, then this must also be even, right? So even and the sum of the degrees of the vertices of even degrees is also even because this is the sum of the degrees of all the vertices of odd degrees in graph. So there must be an even number of such vertices, right? Because if we have odd number of odd vertices, then sum of degrees won't be equal to an even number, right? So this must be an even. So this is the proof. An undirected graph has an even number of vertices of odd degree. The next definition. So before defining the next definition, let's have a look at directed graph definition of directed graph. A directed graph G consists of V, a non-empty set of vertices, and E, a set of directed edges or arcs. Each edge is an ordered pair of vertices. The directed edge UV is said to start at U and end at V. Now let UV be an edge in G, this directed graph. Okay, UV be an edge in the directed graph G. Then U is the initial vertex of this edge and is adjacent to V. So U is called adjacent to V in this pair. This is an ordered pair. And V is the terminal end vertex of this edge and this is adjacent from u. Okay, adjacent to and adjacent from. Adjacent to, initial vertex is adjacent to the terminal vertex, and the terminal vertex is adjacent from the initial vertex, right? So the initial and terminal vertices of a loop are the same. Now, after defining a degree of a vertex, now we are going to define in degree and out degree of a vertex. The in degree of vertex, denoted by degree -v, is the number of edges which terminate at V. Okay, all the edges whose terminal end is V, the number of such edges is called the in degree of V. And the out degree of V, denoted degree plus, is the number of edges where V as the initial vertex, right? Know that the loop at the vertex contributes 1 to both the in degree and out degree of the vertex. So there is an example, uh, in degree of A. Now in degree, where the number of in degree is the number of edges which terminate at V. So how many edges are terminating at A? So here we go, 1, and loop itself, so 2. So in degree is 2. Okay, so in degree of B, this is the edge B. In degree, here is the edge which ends at B, this is another edge which ends at B, so the in degree of B is also 2. So in degree of F, since F is an isolated vertex, so in degree of F is 0. Okay, and out degree of F is 0 as well, because this is an isolated vertex. Now degree, out degree of A, out degree of a vertex means the number of edges for which V is initial vertex. Okay, so out degree of A, initial vertex for this edge 1, initial vertex for this edge 2, initial vertex for this edge 3, right? And initial vertex of this 2, so 4. Total number of edges is 4. And similarly, you can find all the degrees of other edges. And degree of F is 0, we have already discussed, because this is an isolated vertex. Next theorem, let G be a graph with directed edges. Then in degree of a vertex V, where V belongs to V, sum of all the in degrees where V belongs to V is equal to the sum of out degrees for all the vertex V belongs to V, and this is equal to the number of edges. Okay. Now, special types of simple graphs and complete graph. Okay, a complete graph on n vertices, denoted by Kn. So complete starts from C, but the notation is K. So complete graph on n vertices, denoted by Kn, is a simple graph that contains exactly one edge between each pair of distinct vertices, right? So this is the graph K1 with the vertex 1. This is the graph for K2, that is for 2 vertices. This is K3, this is K4, so this is K5, and similarly this is K6. So all are simple graphs joining all the vertices, all the n vertices. There are more special types of simple graphs. So cycle Cn. The name starts with C, and the notation is also Cn, right? So that is why in the previous slide we have Kn, because it would have confused if every type of graph starting from C denoted by Cn. So that is why complete graph is denoted by complete graph denoted by Kn. Now cyclic graph denoted by Cn. So n greater or equal to 3 consists of n vertices v1, v2, vn, and the edges joining v1, v2, v2, v3, and so on, vn, v1. So we will start from joining v1, v2. v2 will be joined with v3, and v3 will be joined with v4, and so on. vn will be joined with v1. So this type of graph is called a cyclic graph. So this is C3. The first vertex is joined to second, second to third, and third to one. Okay, so no more lines, extra line. So first joined to second, second to third, third to fourth, and so on. So first to 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. I mean 6. Do we have 3? No, 5 to 1. 5 to 1. So nth must be joined to 1. So similar is the case 1, if this is the vertex 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 1. Okay. So this is the cyclic graph. Now next wheel graph. W1 denoted by W1 is obtained by adding an additional vertex to a cyclic graph Cn and n greater or equal to 3 and connecting this new vertex to each of n vertices in Cn by new edges. So these are Cn. So just insert one vertex inside the graph and join every vertex to this vertex. So we have wheels. So this is V3, this is V4, this is V5, and this is V6. W, sorry. We have wheel graphs W3, W4, W5, and W6. Okay, special types continues. Now n-dimensional hypercube. Hypercube. So n cube is denoted by Qn, is a graph of 2 to the power n vertices representing all bit strings of length n. So the property of Qn is that it has 2 to the power n vertices representing all bit strings of length n, where there is an edge between two vertices that differ in exactly one bit position. So we have, if we have Q1, that is we are going to join the bit strings of length 1. So bit strings of length 1 are 2, 0 and 1. So this is the graph. Now Q2 means we are going to join the bit strings of length 2. So bit strings of length 2 are 4. So this is the Q2. And similarly, Q3 can be drawn like this. Bipartite graph. A simple graph G is bipartite if V can be partitioned into two disjoint subsets V1 and V2 such that every edge connects a vertex in V1 and a vertex in V2. In other words, there are no edges which connect two vertices in V1 or in V2. Okay, so it is not hard to show that. An equivalent definition of bipartite graph is the graph where it is possible to color the vertices red or blue so that no two adjacent vertices are of same color. So this is an example. There is the graph G, this is the graph H, and the question here is graph G and H displayed in this figure are bipartite or not. So let's see. Graph G is bipartite because its vertex set is the union of two disjoint sets A, B, and C. A, B, and C. They are not connected with each other. Okay. A, B, and C. Similarly, we can find C, E, F, and G. They are not connected with each other. C, E, F, and G. Okay. So C, E, F, G are in blue color, and A, B, D are in red color. So this is the set of disjoint this is the set of this is a disjoint two disjoint sets of vertices. Now A is connected to E. That is, a vertex from this set is connected to the vertex of this set, but they are not connected with each other within the set, right? Similarly, B is connected to C, B is connected to E, B is connected to F, B is connected to C, okay, and so on. And each edge connects a vertex in one of these subsets to a vertex in the other subset. So this is G is bipartite. Now, what about graph H? So in this graph, we cannot find such two disjoint sets. So H is not bipartite. Since if we color a red, then the adjacent vertex F and V must both be blue. Okay, so let's go ahead. C6 is bipartite. C6. So what was C6? It was a cyclic graph uh, with 6 vertices, right? So we can find the disjoint sets V1, V2, V3, and V1, V3, V5, and V2, V4, V6. That is odd number, odd subscripts, and even subsets. So C6 is bipartite. K3 is not bipartite, so this is the figure for K3. So we are not able to find two disjoint sets such that they are not connected with within the set, and they are connected to each other. Special types of graph and the computer network architecture. So ways special graph play an important role in the design of computer networks. So first graph in the figure A is called star topology. So some local area networks use a star topology. It looks like star, which is complete bipartite graph K1n as shown in this figure. All the devices are connected to the central control device. Okay, all the devices are connected to this central control device. There is another example of local networks which are based on ring topology. This is called ring topology, where each device is connected to exactly two other using Cn, all illustrated in B. Okay, so every device is connected to exactly two other devices. So messages may be sent around the ring. Now, other in C is actually union of these two, and this is VN based. WN based. I don't know why I call it V. This is wheel W. So WN based topology, combining the features of star and ring topology. So various special graphs also play a role in parallel processing, where processors need to introduced as one processor may need the output generated by another. So we have n-dimensional hypercube, n-cube, that is Qn is common way to connect processors in parallel processing Intel hypercube. And other common method is the mesh networks, which is shown in this figure. And in this mesh network, 16 processors are connected. Bipartite graph continues. We have 4 more examples on bipartite graph. So show that C6 is bipartite, and I think I have already shown it. Huh? Yes, so it is repeated. C3 is not bipartite. C3 is just like K3. So K3 is not bipartite, so C3 is also not bipartite. Now, a complete bipartite graph, KMN, is a graph that has its vertex set partitioned into two subsets, V1 of size n and V2 of size n, such that there is an edge from every vertex in V1 to every vertex in V2. Okay, so these are the examples of complete bipartite graphs. This is K2, 3. This is the set of two vertices. This is the set of three vertices. Now each vertex is connected to the all the vertices from the other set. Similarly, you can see this is connected to all the vertices. Now let's check this. This is connected to every vertex from this set. This is connected to every vertex from this set. This is connected to every vertex from this set. And similarly, you can find others as well. This is K3, 3. This set consists of three vertices. This set consists of three vertices. Now start joining every vertex to every vertex of the other set. So you will have a complete bipartite graph denoted by KMN. Bipartite graphs are used to model applications that involve matching the elements of one set to the elements in another. For example, job assignments, vertices represent the jobs, and the employees edges link employees, jobs and employees, and edges link employees with the those jobs they have been trained to do. A common goal is to match jobs to employees so that the most jobs are done. Okay, so here are the candidates, employees, and these are the jobs. Okay, so these are connected. So marriages on an island, vertices represent the men and the women, and edges link a man and a woman if they are an acceptable spouse. We may wish to find the largest number of possible marriages. Okay, next subgraph, just as a subset. Subgraph of a graph G is a graph WF where W is contained in V. V is the set of edges. So if W is the subset of V, that is the V is the set of vertices. Sorry, V is the set of vertices, and W is the set of subset of V. Okay, so we can skip few of the vertices. Then we have a subset of V, and F is the subset of E. E is, are the edges, set of edges. So F is subset of E. A subgraph H of G is proper subgraph if of G if H is not equal to G. Okay. So here we have an example of subgraph. G be a simple graph, the subgraph induced by a subset W of the vertex V is the graph WF where edge set F contains an edge in E if and only if both endpoints are in W. So here we show that K5 is a subgraph induced W. A, B, C, D, induced by W, A, B, C, D, E. So this is the W, A, B, C, D, E. And this is the subgraph A, B, C, E, which is induced by W. Now union of two simple graphs, G1 is a graph which is simple, G2 is a graph which is also simple with the vertices V1 and V2 respectively. So the union of these two simple graphs is the simple graph with vertices, set of vertices V1 union V2 and the set of edges E1 union E2. The union of G1 G2 is denoted by G1 union G2. So if we have a graph like this, if we have a graph like this, and then union will look like this. Okay, you can see. So we actually draw common edges of course one time, just like union of sets. So this is the common edge between these two graphs. So this is it comes only once. Similarly, this is the common edge, so it is drawn only once. So this is the union of these two graphs. So there are few questions from exercise. Question number 13. What does the degree of a vertex represent in an academic collaboration graph? What does the neighborhood of a vertex represent? And what do isolated and pendant vertices represent? So, what does degree of vertex represent in an academic uh, collaboration graph? So person is joined by an edge to each of his or her collaborators. So collaboration graph, vertices are persons and edges are the collaboration between the persons, right? So the degree of V is the number of collaborators V has. Similarly, the neighborhood of a vertex is the set of co-authors with the person represented by the vertex. And an isolated vertex represents a person who has no co-authors, right? And a pendant vertex represents a person who has published with just one other person. So if a vertex is connected to just one other vertex, then that vertex is called pendant vertex. So there is another example. Determine the number of vertices, edges, and find the in degree and out degree of each vertex of the given directed multigraphs. So here is the graph. This is question number 7 in your book. So this is directed graph as we are told in the question. So first of all, what we need to determine number of vertices. So it has 1, 2, 3, 4 vertices, okay, and the number of edges. So number of edges 1, 2, 3, 4, 5, 6, and 7. So we have 7 edges. And what else is required? In degree and out degree of each vertex. So let's start with A. So in degree of A. The terminal edge, the terminal vertex for this edge is A, so 1. The terminal vertex for this edge is also A, that is 2. And the terminal vertex for this loop is also A, so in degree is 3. Okay, so out degree of A. Out degree of A, that is the starting vertex. A is starting vertex for this loop only. So the in degree is, the out degree is 1. Similarly, let's try in degree and out degree of C. So in degree of C, that is, this is the terminal end of this edge. This is terminal end of this edge. So in degree is 2, and out degree, this is the initial end of this edge. Okay, so out degree is 1. So this is how we can find the in degree and the out degree. So what about the vertex C? So since a vertex C is an isolated vertex, so its in degree and out degree is 0, right? Next question, how many vertices and how many edges do the graph Qn have? Now, since the vertices of Qn are the bit strings of length n, and they are 2 to the power n vertices, each vertex has degree n. Since there are n strings that differ from any given string in exactly one bit, so the sum of the degrees is n multiplied by 2 to the power n. Since this must be equal to twice the number of edges by the handshake theorem, so we know that there are n to the power 2n divided by 2, that is n to n minus 1 edges. Okay, so that's all for today's lecture, and in we'll see you on Wednesday, that is tomorrow, for your questions or any queries regarding this video. Till then, take care. Bye bye.